All right, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is empirical and molecular formulas. Now, before we get going into notes, there's just a couple of objectives I want to outline for this particular video. Objective number 1, explain what is meant by the percent composition of a compound. And objective number 2, determine the empirical and molecular formulas for a compound from mass percent of actual mass data. So let's get going in notes here with the concept or the term of percent composition. And so percent composition is just defined as the percent by mass of each element in a compound. And now something to keep in mind is that the percent by mass of any element in a compound can be found by dividing the mass of the element by the mass of the compound and then multiplying by 100. Now, we can also put that same thing that I just wrote down into a formula version. So I'm going to put percent composition is equal to the mass of the element divided by the mass of the compound and then multiplied by 100. Now, an important thing to keep in mind as well with this is that the percent composition of a compound can also be determined from its chemical formula. All right, so let's go through a ways or steps that we can find the percent composition of a particular element in a compound. So we'll shift gears here and we'll head to page 2 of the notes. And the first step is to determine the molar mass of the entire compound. The second step is to write down the mass contribution of each element. In other words, how many grams of each element are in the compound. The third step is to divide the mass of each element in the compound by the molar mass of the entire compound and multiply by 100. The fourth step is to calculate and show the correct units, which is the percent of each element. All right, so now we're going to put those steps to the test in our example. So our problem here says determine the percent composition of each element in baking soda or sodium bicarbonate. So the first thing that we need to do is we need to determine the molar mass of the entire compound. So I'm going to list out each and every substance involved in our sodium bicarbonate. So we have sodium, hydrogen, carbon, and oxygen. And so the first thing to do, remember when we're finding the molar mass, is find each element. So Na, you round that to 2 decimals, so this becomes 22.99 grams per mole. So 22.99 grams per mole. You multiply it by how many sodiums you have in your formula, which is just 1. So that means sodium contributed 22.99 grams per mole. Then you go down to hydrogen. Remember, hydrogen is the weird one. I like to round to 3 decimals. It's the only one there. And so the molar mass is 1.008 grams per mole. Again, we multiply it by how many hydrogens are in our formula, which is just 1. So again, this just contributes 1.008 grams per mole. And then we go down to carbon. Carbon, if you find it on the periodic table and you round it to 2 decimals, would be 12.01 grams per mole. You multiply that by the number of carbons in our formula, which is just 1, and you have 12.01 grams per mole. And then our last atom here, or element, is oxygen. And remember, oxygen rounds to exactly 16.00 grams per mole. And you multiply it by the number of oxygens in our chemical formula. So you multiply it by 3. 16 times 3, you can punch it into your calculator, but 16 times 3 is 48 grams per mole. Now all I'm going to do down in the bottom here is I'm going to add all of these numbers together. So in my calculator, I am going to type in 22.99 plus 1.008 plus 12.01 plus 48.00. I'm going to press enter. Well, I get a value. I'm going to round to 2 decimal places. So I'm going to round to 84.01 grams per mole. So this is 84.01 grams per mole. Now, this is really important here. We've just gone through step 1. And so what I am going to do is I'm going to divide each and every mass that we've just added up here by that molar mass. So I know the space is kind of tight here, but what I'm going to do here is I'm going to divide the total mass contributed by each element. So in the case of sodium, is going to be 22.99 grams per mole divided by the entire molar mass of the entire compound. So in orange here, I just divide this number by 84.01 grams per mole. I then multiply this by 100 and I punch it into my calculator as follows. So to find the mass contributed by sodium, I'm going to take 22.99 divided by the total mass of the compound, which is 84.01. I'm going to press enter, and then I'm going to multiply by 100. Now, because I had 4 digits in my answer, I'm going to round this to 4 total digits. So the mass contributed by sodium is 27.37%. So the mass of sodium contributes 27.37% of our total compound. Now, we move on here and we do the same exact thing for hydrogen. Again, the total mass contributed of hydrogen is 1.008. We are going to divide this by the molar mass of the entire compound, which is 84.01 grams per mole. Multiply that value by 100. And in my calculator, I'm going to type in the mass contributed from hydrogen, so 1.008, divided by the total molar mass of the compound, which is 84.01. You press enter. You multiply that number by 100. And again, we write down 4 total digits. So this would round to 1.200% of hydrogen. So what that means, again, as I write this, 1.220. Again, that is 1.22% of this entire compound is composed of hydrogen. Now we do the same thing for carbon. We divide the total mass of carbon, 12.01, by the total molar mass of the compound, which is 84.01 grams per mole. We multiply that by 100. And again, in my calculator, what I'm going to type in is 12.01 divided by 84.01. I press enter, and I multiply that by 100. So I round to 4 total digits, which gets me 14.30% of this entire compound is carbon. All right, so the last thing that we need to do, we need to take the mass contributed by oxygen, which it contributed a total of 48 grams per mole, and we need to divide it by the molar mass, which is 84.01 grams per mole, and then we multiply this by 100. So all I'm going to do, the mass contributed by oxygen was 48. We divide that by the molar mass of the compound, which is 84.01, and we press enter. We multiply that by 100, and we write down 4 significant digits, which would be 57.14. Okay, so we have 57.14% of this entire compound is composed of oxygen. So again, if you add these up, it's just slightly over 100, and that's due to our rounding on our molar mass. But you can see this is the percent that each element contributes by mass in our particular compound. So that's how we would go about, and we would go through this process. Now what we're going to do here is we're going to shift gears a little bit to some different terms. And those terms are empirical and molecular formulas. So we start out here with empirical formula. And the empirical formula is just defined as the smallest whole number mole ratio of the elements in a compound. And the reason that we just learned about percent composition is that to get an empirical formula, they use data from experiments that allow us to get the percent composition, and then from that data we can get the empirical formula. So that's how all this ties together. And so there's important things to remember with the empirical formula. One of which is that the empirical formula may or may not be the same as the molecular formula. Now, I'm not going to get into the molecular formula right here because we talk about it just below in our next section. But another important point here is that the empirical formula must be used to determine the molecular formula of a compound. And then our last important thing here is that the empirical formula is used to calculate the molecular formula. Okay, so now we can shift gears to what the molecular formula is. And we've already mentioned it above, but we'll get into the details here. So the molecular formula is defined as the actual number of atoms of each element in one molecule or formula unit of a substance. And so something to remember with molecular formulas is that they are always a whole number ratio or multiple of the empirical formula. Alright, so now that we have the basic definition of empirical and molecular formula, let's go through steps to be able to determine how we can find the empirical and the molecular formula. So we'll shift gears here. And on here I have steps to determine the molecular formula of a particular compound. Well, you can also add to this the empirical formula, because to be able to find the molecular formula, you have to first be able to identify the empirical formula. And so you actually do or get to the empirical formula by going over these particular steps. So the first step is to convert the percent composition of each element to grams of each element. The second step is to convert the grams of each element to moles. The third step is to divide each of the number of moles from step 2 by the smallest of the calculated moles. Once you do this, step 4, what it needs you to do here is to examine the mole ratio calculated and ensure each number in that mole ratio is a whole number. If for whatever reason you don't have a whole number, you need to multiply to get to a whole number. Now, if you need to multiply something by a number to actually get that mole ratio in a whole number format, you need to do it to everything. Think like algebra here. So I'm going to put here preform to all elements. Better term for that is apply to all elements. In step number 5, once you have all the moles in a compound, you need to determine the empirical formula. So how you do that? The whole numbers that you determine in step number 4 become the subscripts of the formula in which you're trying to find. Okay, so for step 5 here, if you were just finding the empirical formula, you would actually stop at step number 5. Now, to determine the molecular formula in steps 6, 7, and 8, what you need to do is this. You need to perform the following calculation. You need to take the given experimental mass and divide it by the empirical formula mass. And what you'll get here is a whole number, very close to a whole number, and you are going to use this whole number to be able to multiply the subscripts of the empirical formula by this number that we will call the number n. Instead of using the number sign here, we will say that this is n for some number. So again, multiply this number n by the subscripts in the empirical formula. Now, once you multiply those subscripts by that number n, you will rewrite the formula to have the molecular formula. So we'll go over a couple of steps. We'll do one example where we just stop at the empirical formula, and then we'll go all the way down to finding the molecular formula. All right, so going through this process here, we have... Okay, so we have our example here where we're just determining the empirical formula. So that means we're going to stop at step number 5 there that we just went over. And we want to determine the empirical formula for methyl acetate, which has the following chemical analysis. It has 48.64% carbon, 8.16% hydrogen, and 43.20% oxygen. So the first thing that you're going to do is just write down the percent of each of these elements. So we have 48.64% carbon. We have 8.16% hydrogen. And we have 43.20% oxygen. And all we need to do here is we convert percent to grams. So we literally just take the percent sign and we change it to grams. So now we have 48.64 grams of carbon. We now have 8.16 grams of hydrogen. And we also have 43.20 grams of oxygen. Now that's step 1. What we need to do now is we need to go from grams of this substance to moles. So we're going to go one element at a time. So we have grams of carbon on bottom. We want to go to moles of carbon. And so where we find that gram to mole ratio is the periodic table. Now, on the periodic table, it says there's 12.01 grams per 1 mole. Again, 12.01 grams per 1 mole. So our grams goes on bottom. Now, we plug this into our calculator, and I'll show you what to round to. So we have 48.64 divided by 12.01. We press enter, and we're going to keep 2 decimals. So we're going to go 8.05 moles of carbon. Okay, now we need to convert grams of hydrogen into moles of hydrogen. So we cancel out grams of hydrogen on bottom. On top, we have moles of hydrogen. Again, we get that gram to mole ratio from the periodic table of elements. We look up hydrogen. Hydrogen's the weird one. I want to round to 3 decimal places. So that's 1.008 grams per 1 mole. So again, 1.008 grams per 1 mole. We turn to our calculators and we go through this. So we have 8.16 divided by 1.008. We press enter. And again, we're going to keep 2 decimals. We'll have to do some rounding here, but this rounds to 8.1 moles of hydrogen. We do the same exact thing for oxygen, where we want grams to cancel out. We want to convert to moles. We find that value for grams down here on the periodic table, and it rounds to exactly 16.00 grams per 1 mole. So in our calculator, all we're going to do is we're going to hit 43.20 divided by 16.00. We hit enter. We get a value of 2.7 moles of oxygen. Now, this is kind of the weird step, and I always like to cover up everything that I've done. I look at these numbers here on the right side so far, and I ask myself, okay, what of these numbers is the smallest? Well, the answer is 2.7. So this kind of awkward step means or says that we have to divide everything by the smallest number of moles. So everything gets divided by 2.7. And we'll start from the bottom up since that will be easiest here. 2.7 divided by 2.7 is just 1 mole of oxygen. 8.1 divided by 2.7. So 8.1 divided by 2.7. Press enter. Look at that. That gives us a whole number of 3. So this means 3 moles of H. And then 4.05 divided by 2.7. So 4.05 divided by 2.07. We get a value here. We get a value here very close to 2. And so what we can do here, and made a very costly mistake. I said 2.07. This is 2.7. Okay, so slow down here. This is 4.05 divided by 2.7. That's better. 1.5 moles of carbon. Okay, now ask yourself these numbers right here. Have you ever seen a decimal in a chemical formula? The answer is no. So what you need to do, and the one holdup here is our carbon. What you need to do is ask yourself, what times 1.5 would equal a whole number? So if you don't know where to start, just start by putting in numbers, and we'll start by multiplying it by 2. Looky there. Just by multiplying it by 2, we get a whole number. So what we did here is we made this a whole number by multiplying it by 2, and now we have 3 moles of carbon. But just like in algebra, what you do to one thing here, you have to do to everything else. So since we multiplied carbon by 2, we have to multiply hydrogen by 2. So 3 times 2 gives us 6 moles of H, and 1 times 2 gives us 2 moles of O. All right, so now these final right-hand numbers allows us to write down the empirical formula. So the empirical formula is this. You just write down the elements, their symbols in order that you see them or order that they appear. So we're going to write down carbon, and then the subscript is this furthest right number, which for carbon is 3. And you write down the next element, which is H for hydrogen, and that furthest right number is 6. And then you write down the last element, which is O, and the furthest right number for O is 2. And so the empirical formula for methyl acetate becomes C3H6O2. All right, so now we can transition to finding the molecular formula and going a few steps further. Shift gears here, and we're going to do another similar problem, but we're going to go a little bit further, and we're going to find the molecular formula. Now, I'm not going to do the rounding business, and I'll show you how that stuff works. That might have been a little confusing at first, but I am going to, again, not round, and I'll point that out when I go through this. But we have a chemical analysis of succinic acid, which is composed of 40.68% carbon, 5.08% hydrogen, and 54.24% oxygen. It also has a molar mass of 118.1 grams per mole. What is the empirical and molecular formula of succinic acid? So again, we start out and we just write down the percent. So we have 40.68% carbon. We have 5.08% hydrogen. And we have 54.24% oxygen. And the next step here is you just take percent to grams. So this is going to become 40.68 grams of carbon. This will become 5.08 grams of hydrogen. And this will become 54.24 grams of oxygen. Okay, now we need to go from grams of our substance to moles. So what we're going to do first is we're going to have grams to moles of each and every element. So again, all we need to do to find that number of grams is we look on the periodic table. For carbon, we round to 2 decimal places, and that becomes 12.01 grams per 1 mole. So we have 12.01 grams per 1 mole. And what I'm going to do here is not round. So it may be kind of confusing. I went a little bit further into detail there. All I'm going to do is take 40.68 divided by 12.01. And I'm just going to write down 2 decimals. So this is 3.39 moles of carbon. So I'm just going to write down what I see. So again, you can just do that for that first step. If that was confusing on that last problem, you just write down what you see in your calculator. Now we need to do or go from grams of hydrogen to moles of hydrogen. So we set up our conversion and we go through this process here. Remember, hydrogen, I like to use 1.008 grams per 1 mole. So 1.008 grams per 1 mole. Again, we set this into our calculator. So we take 5.08 divided by 1.008. And I'm just going to write down what I see. So I'm going to write down 5.04 moles of H. Now we do the same thing for oxygen. So we need to go from grams of oxygen to moles of oxygen. And so we go through this process here. We first look up what is the molar mass. Well, the molar mass of oxygen is 16. And so we write down 16.00 grams per 1 mole of oxygen. Now, we type that into our calculator. So we type in 54.24 divided by 16.00, and I write down exactly what I see in my calculator. 3.39 moles of O. So again, I know I did some rounding and some weirdness there. Write down 2 decimals, whatever this is, for this first gram to mole, or step 2, just write down what you see. What we need to do here, this is kind of the weird step. We look at the numbers that we've just found, and we ask ourselves, what is the smallest of these numbers? Well, if you look here, there's 3.39, 3.39, and 5.04. Well, of those numbers, 3.39 is the smallest, and so it doesn't matter where we start here, but we have to divide everything by 3.39. Okay, so it's really easy here because 3.39 divided by 3.39 means that we just have 1 mole of oxygen. Now, up here, 3.39 divided by 3.39 means that we just have 1 mole of carbon. Okay, and over here, we're going to have to go to our calculator, but we're going to do 5.04 divided by 3.39. We press enter, and we get a value here of this. Now, on this last problem that we did, we went ahead and we rounded that to 1.5. So let's go ahead, let's do the same, and I'll show you why that is important here in a second. The reason that it's important is this. Again, obviously that is nowhere near close to a whole number. So what we have to do here is this. We have to think to ourselves, what times 1.5 would get us a whole number? Again, always start with something like 2, 3, 4. And look, if we multiply 1.5 by 2, we get exactly a whole number of 3. So we have to multiply this by 2. So that gives us 3 moles of H. And what we do to one thing, we have to do to the other. So because we multiplied H by 2, we have to multiply carbon by 2. So that means 2 times 1 gives us 2 moles of carbon. And then we also have to do that to our oxygen. So we multiply 1 times 2. That is 2 moles of oxygen. Now, this final right-hand side number gives us our value for our empirical formula. So our empirical formula is this, okay? It is, you just start out with what the first element is, carbon. The subscript becomes the number of moles there, 2. Hydrogen is our second element, so we write that down. The subscript here would be 3 because that's that final number to the furthest right. Oxygen is our third element. We have 2 oxygens, and we've found our empirical formula. Okay, so that's one part of the answer. That would be through step 5 on our steps we just went over. Now what we need to do is we need to figure out the molecular formula. So what we need to do now is we need to calculate the molar mass of our empirical formula. So what we do is we just list out everything that we have, so carbon, hydrogen, oxygen, and we go through this particular process. Carbon, we first start out by writing the molar mass. Well, looky here. The molar mass of carbon is 12.01 grams per mole. And if you forget, it's also on the periodic table, but it's 12.01 grams per mole. And you multiply that by the number of carbons in your empirical formula. So we multiply that by 2. So 12.01 times 2, 12.01 times 2 gives us a value of 24.02 grams per mole. Now we do the same thing for hydrogen. What's nice here, we have hydrogen's molar mass of 1.008, but if you forget, 1.008 grams per mole is our value. We multiply it by how many hydrogens we have. We have 3. So if we take 1.008 times 3, we get 3.024. We're just going to round that to 3.02. So we get 3.02 grams per mole. And then oxygen. Remember, oxygen has a molar mass of 16 grams per mole. If you forget, remember it's on here, the periodic table of 16 grams per mole. And we multiply it by the number of oxygens we have, which is 2. 16 times 2 is 32. And all we need to do is add these values together. So we add 24.02 plus 3.02 plus 32.00. We get a value of 59.04 grams per mole. Okay, that is the empirical molar mass. So what we're trying to do is we're trying to find this ratio where we take the given molar mass. Okay, so given molar mass divided by empirical formula, and I'm going to abbreviate that as EMP formula. Molar mass, for space purposes, I'll just say MM. Well, in the problem, if you look here, we had a given molar mass of 118.1 grams per mole. We divide it by that empirical formula that we just found. So that empirical formula that we just found is 59.04 grams per mole. We put that into our calculator. Now, we will just get a ratio, and a ratio means that we do not have a unit in this case. And look here, this number, when I put it into the calculator, is very, very, very close to 2, and so we could call this 2. Now, what this means is that we need to multiply everything in our empirical formula, or our subscripts in our empirical formula, by 2. So, I'm just going to do this. C2H3O2 was our empirical formula. And I'm going to say, hey, we need to multiply this by 2. So when we write our molecular formula, we would have this. We'd have 2 times 2. So this means we'd have C4. And then we'd have H, 3 times 2, which would be H6. And then we'd have 2 times 2, O4. So in this case, this right here that we just found would be known as our molecular formula. Okay? Now, this has been a lot of math. Remember, the key thing here is in this first mole conversion, just go ahead and keep 2 decimals. I know I rounded kind of awkwardly on that last one. Just go ahead, keep 2 decimals. That makes life a lot easier for you in going through this process. But at the end of the day, you should end up with everything with whole numbers. You should also remember that what you do to one thing, you have to do to every other element involved in this particular type of problem. So, there has been a lot of math here. It's kind of a lot to observe and take in at first, but take your time, go through these particular steps, and I hope you have enjoyed this episode, and like always, subscribe.